Hello everyone, welcome back. This is lesson 5 of Machine Learning Zoomcamp session 8, and in this lesson we will talk about transfer learning. In the previous lesson we talked about the internals of convolutional neural networks. We talked about convolutional layers, and the main purpose of convolutional layers is to convert an image into a vector representation. And then we talked about dense vectors. The reason we need dense vectors is they take vector representations and use it for making predictions. And in this lesson, we will see how we can use a neural network that is already pre-trained. Now, this is a neural network that we already have. So this is a neural network that was trained on ImageNet dataset. So remember we talked about that each layer contains a bunch of filters. These filters are learnable. The model learns these filters during training, and the filters it learns, they are quite generic. These filters can be used for many purposes. Somebody trained this model on ImageNet, so they trained all this bunch of filters, and the model learned to take the image, any picture, and convert it into some vector representation. This is quite generic, and we don't really need to change it for our task. But actually, training these filters in the convolutional layers is very difficult. You need to have a lot of images. So a model needs to see a lot of images to come up with filters that make sense. So the model needs to see a huge amount of images to be able to come up with filters like that. Then we have a bunch of dense layers. After we converted our image into vector representation, we have a bunch of dense layers for making the final prediction. And these dense layers, they are specific to the dataset. Remember, we talked about that in ImageNet, there are 1,000 different classes. So that's why the output it has here contains, like it's a dense layer, the size of 1,000. This is quite specific to this particular data set, and we usually don't need it. So let's say in our problem, we want to predict only 10 classes, and many of these classes, like for example, t-shirt, they don't even exist in ImageNet. So we don't need them. So the vector representation that we have from ImageNet is quite useful, but the dense layers are not. So what we want to do is we want to keep the convolutional layers, but we want to train new dense layers. And this is the idea behind transfer learning. The model was already trained, already has all these convolutional layers, all these filters. So we just reuse that and build on top of that. And we throw away dense layers from ImageNet and have our own dense layers. This way, everything that the model learned previously, the most difficult part, can be reused, and we're kind of transferring this knowledge to a new model. This is the main idea behind transfer learning. So let's see how we can do it with Keras. To be able to do it with Keras, the first thing we need to do is actually read our dataset. For that, there is a special class called image data generator that lets us read images from whatever place where we start and use them for training. This class image data generator lives in TensorFlow Keras preprocessing image. Then the class is image data generator. So then let's have it for training, image data generator. And the only thing we need to specify right now is the preprocessing function. This is the same function we used previously here, preprocess input. And that's all we need for now. And then from this generator, we can say we want to read from the directory. So we use this method flow from directory to read from a directory. In our case, the directory is this closing dataset small train. Then target size is, for now, let's have a small image. The images they will be 150 by 150. This way we can experiment faster, because if we have images that are 299 by 299, training them will take 4 times more, because this 299 by 299 is 4 times bigger than this one. It's just 1/4 of this big one. For experiments, just to train model faster, we will use smaller images, and then at the end we will retrain on bigger images. So that's target size, and then the last thing we want to specify is batch size. Batch size is how many images at once we read. So it will not be just one image, but it will be multiple. however many we want. Let's say 32 images. So it means that we'll have 32 images. This is our batch. We'll have 32 images. Each image will be 150 by 150. And remember that we also have 3 channels. So the shape of our batch will be 32, 150 by 150 by 3. And then our batch will go through convolutional layers. And then we will have 32 vectors, 1 for each. And then we will have 32 different predictions at the end. Here we specify the batch size, let's say 32, and that's all we need. So let me just format it a little bit and name it train dataset. And it says in this folder, in the train folder, it found 3068 images, and there are 10 classes in total. What we can see now is we can see what kind of classes are there. So I think it's something like class indices. Yeah, so it says the first class is dress, then hat, then long sleeve, outwear, pants, and so on. And t-shirt is the last one. So these are the classes, and these are the same as folders in this closed-in dataset train. We have the same classes here. So it inferred the names of the classes from the folder structure. So everything that is inside the folder t-shirt, it put under the t-shirt class. Then we can actually look inside, take a look at what this train dataset generates. So this is a generator or iterator. So to be able to get the next batch, need to use this next function. Or when we do a for loop internally also invokes this next function. So let's do that. Train data frame. Actually, it returns 2 things. It returns X and Y. So it returns our features, images, and then Y labels. So let's take a look at X. So this is very similar to what we saw previously. So it loads an image, a bunch of images actually, and applies this preprocess, this preprocess input function because we asked it to apply it. And if we look at the shape, then it's 32 by 150, 150, and 3, exactly like we wrote here. Let's also take a look at Y. I'll just look at the first, let's say 5. This is how our target variable looks like. And let me just quickly check how our classes look like. So here, the labels that we have, it used one hot encoding for the labels. For example, in this column, we have t-shirts. So this is index number 9. So here we have t-shirts. And for example, the first one is dress. We don't have any dresses here. So this one is 0, 1, 2, 3, 4, 5, 6, 7, 9. So the fourth one is pants. This row here has label pants, and this is one hot encoding. So it has 1 for pants and then 0 for the rest. This is the same one hot encoding method, but applied to target variable. This is how we usually do multi-class classification. And you can also think of this as 10 different binary variables. So this one 4 says if this, the observation 0 if this is not pants, and 1 if it's pants. And then we have just 10 different variables, 10 different binary variables, and then we sort of fit 10 different models, even though we actually fit only 1. But you can conceptually think as if we're fitting 10 different binary classification models, and each is predicting if it's dress or not dress, and then if it's pants or not pants, or if it's t-shirt or not a t-shirt. And this is how our data looks like. We can do now the same for validation. I'll just put it into one cell so it's easier to copy. And then I call it validation generator, validation dataset. And here we read from the validation folder, and the rest is the same. So target size and batch size. Here, one thing we can add is maybe we don't shuffle it. So by default, it shuffles the dataset. But for validation, since we only use it for validating, it doesn't need to shuffle actually. It's okay if the images come in the same order every time. So we execute that, and it says that it found 341 images from 10 classes. So the same 10 classes we had previously. We know how to read the data. Now let's train a model. For that, let's create a model. We'll call it base model. What do we want to do now? Let me copy it. So we have our model from trained on ImageNet. So we keep the convolutional layers. So this will be our base model. And then we'll train our custom model on top of that. And then this will have 10 classes t-shirt. And base model in our case is exception. So we'll use exception to extract the feature representation from the image, and then we will train the rest. So let's create our base model. It's exception. Then we say that the weights are ImageNet. It's ImageNet. Then other thing we say here is we only want to keep convolutional layers, and parameter for that is include top false. So actually in Keras, it's a bit different. Conceptually, it's the same, but the way they mentally arrange a neural network is slightly different. So it goes from the bottom to the top like that. So here we have bottom, then we have convolutional layers. So then we get our vector representation. Then finally, we have a bunch of dense layers and our prediction. So this part over here in Keras terminology is called top, and this one is bottom. And when we say include top false, it means do not include the dense layers. So we don't include the dense layers, we only include the convolutional layers. And then the last parameter is input shape, which for us is 150 by 150 by 3. So this is our base model, and we don't want to train this model. So we only want to use it for extracting this vector representation. So what we want to do is we want to say that it's not trainable. So we want to say trainable false, meaning that when we train our model, we don't want to change convolutional layers. Okay, let's execute that. Now it will probably download. Yes, it's downloading this model because previously we were using a different model for larger input shape. So now we have it. And next we want to create a new top. So the first thing we specify here is we need to specify the input, so called inputs. This is the part of the model that will receive the images. So the input here, we know the shape is 150 by 150 by 3. I think it's a bit redundant, but we need to repeat it. This input goes to the base model. This is the input. And it goes to our base model. Let me maybe go to a different screen. So this one is a bit busy already. So this is inputs. And actually, remember that this inputs is a batch. So this is 150 by 150 by 32. And then there are, of course, 3 channels as well. So this is our inputs. So then this input goes to our base model, and we use our base model to extract this vector representation. So base model, and then we apply base model to inputs. This way we say we want to use the base model on inputs, and then whatever is output will be called base. Where we apply base model to inputs, and whatever output is there, we call it base. Let's draw it here. So we apply base model here, and we get something that we call base. You can actually take a look what exactly is there. So let's do that. And for that, we now need to wrap everything into something called Keras model. So let me just say this is the final output of the model. I'll just say the base is the final output. Then I'll create a model, it's Keras model. And then here I need to specify inputs and outputs. So inputs, this is where we feed in the data, and outputs, this is what we get when we call predict model predict. And yeah, so in predict we pass output, and the predictions is, so this input is this X, and this output is what goes here. So it goes this way, this X, our X goes here. And actually remember that our X is a picture of, let's say, t-shirt. So it goes to inputs, then from inputs, it goes to base model, and then from base model, what we will go to these predictions. So let's see what happens. So here we already have something in our X. We can just use that. So let's see what happens. I'm not really sure what warning this is. It's not actually a warning, it's just informational message. It takes some time because I think now it initializes things on the GPU. So the next time I invoke it, it's faster. So let's try to run it one more time. Okay, now it's way faster. And for you in the video, it was probably both times were fast, simply because I edited. I think for me, it took like 30 seconds to run the first one. So let's look at these predictions. So first of all, let's take a look at the shape. What it outputs is it's actually a 4-dimensional thing. I will draw a 3-dimensional cube because I'm not very good at drawing 4-dimensional things. And by the way, the original image we had is also 4-dimensional. Remember, we have channels there as well. So this is our base. It's a 4-dimensional thing. The shape is 32 by 5 by 5 by 2048. This one is actually the size of the batch. If we think about this, actually the right way of drawing this would be this very long thing. And if we talk about just one image. So let's say we have t-shirt here that goes in, not 32 images, but just one. So it passes through convolutional neural network, a bunch of convolutional layers, and that what we get at the end is a thing that has size 5 by 5 by 248. So this doesn't look like vector representation yet because it's actually a 3-dimensional thing. So what we want to do now with this thing is turn it into a vector. So we want to turn it into something 1-dimensional and use that as the vector representation. So we will have something that takes in what we call base and turns it into a bunch of vectors. For that, what we can do is we can take a look at this long 3-dimensional thing and we can just sort of chunk it, slice it, like for every single layer here. So this is 1, this is 0, and so on, up to the very last one. So for each of these things, we can, so like let's say the first one, take a look at this. This is a 5 by 5 thing. So what we can do is we can take the average of this thing and put it in our 1-dimensional thing. And we can do it for every such chunk. So we kind of slice it and take our average and then put it in our vector representation. Then it's again 0, 1, and so on up to the last one. And this operation, when we take something that is 3-dimensional or 2-dimensional and represent it in a smaller dimensionality, it's called pooling. In this particular case, we need average pooling because we take an average of each of these squares. And because we turn a 3-dimensional thing into 1-dimensional thing, so we take like a 2-dimensional chunk here, a square, and take an average. It's called 2-dimensional average pooling. In Keras, this thing for pooling lives in these layers. It's called global average pooling 2D. Let's call it pooling. So we apply this pooling to base and we get back the vectors. And then our vectors would be the output. So what happens here is our input is a t-shirt. Then it goes here to the base model and our base is this 4-dimensional thing, or in case of a single image, it's a 3-dimensional thing like this long. Right? And we want to turn it into 1-dimensional thing. We do it by pooling. So this base goes here. And so this is base and this is vectors. And now the vectors is output. So it goes here, meaning that we will get them in predictions now. So let's see that. So now the shape we have is 32 by 2080, 2048, meaning that we managed to shrink this into 1-dimensional vector for each of the images. So now let's call it pooling. This way is not like what we can do is we can just write this. So we create the pooling and immediately apply it to our base thing. Actually, this way of building a neural network is called functional style. So we use these building blocks as functions. So even though this is actually a model, we just use it as a function, we invoke it, and we pass some input. We say the input to this base model is inputs and the output will be base. Then we create another thing, pooling, and we say the input to the pooling layer will be base and the output is vectors. And this is how we build our neural network. Okay, we're not done yet. We need to do one more thing. So now we have these vectors. Right now we want to have a dense layer on top of that to turn the vectors into predictions. So what we want to have at the end is an array 32 by 10 with the predictions. So I'll call it output because this is actually what we want to output. And yeah, dimensionality of this thing is 32 by 2048. And then in all these cases, 32 is the size of our batch. So let me move them, this thing here. And here for turning vectors into outputs, we want to create a dense layer. Let's do that. It's Keras layers dense, and there are 10 classes, so that's why it's 10. That's why we have 10 here as well, because there are 10 different classes. So we have 10, and then the input to the dense layer is vectors. Right? And if we execute that, now the predictions will be 32 by 10. And to summarize what's happening here, so input is our t-shirt, it goes here, then from input, from there it goes to our base model. Base model takes this as input and produces this three-dimensional long thing. Then from this long thing, we pull it, we turn it to one-dimensional vector by using pooling, and then this gives us our vector representation. Then from this vector representation, we add a dense layer to turn the vector representation into predictions, and the dimensionality of this is 10 because we have 10 classes, and then this is finally what goes to the output of the model. So input is here, and output is what we will have when we invoke predict, right? And input is the X. So let's call this model version 1. Yeah, but now when we do model predict, this actually outputs some nonsense. So if we take a look at this, it just produces some numbers, but of course we haven't trained a model yet. That's why this is just random things, because this layer, when we create it, it's initialized with just random numbers. That's why the prediction is also just a bunch of random numbers. So we actually need to train this model. Training the model, we need a couple of things. So first thing we need is optimizer. So this is the thing that actually finds the best weights for the model. Go back where we discussed the dense layer. So we have these weights, and these weights needs to be trained. How we do this is by changing each element of this matrix and then seeing if it leads to a better solution or not. We do this many, many times. The thing that is doing that changes the weights and sees if it's improving or not is called optimizer. So it doesn't just randomly change, I don't know, this by multiplying it by 10 or setting it to 0 or something like this. It tries to change the weights in such a way that the model actually learns something. So this thing is called optimizer, and the optimizers live in the Keras package called optimizers. There are quite a few of them, of these optimizers, so we'll use Adam. And actually in Keras, there are many optimizers. You can read about them in official documentation, optimizers. So it's keras.io API optimizers. This explains what kind of optimizers are there. For example, this Adam, this is what we are going to use. A really good resource to learn more about these optimizers is again this course CS 231N, which goes into theory, how actually a neural network is able to learn. And optimizer is in the first one, yeah, this optimization part. So it actually says what gradient descent is, and this is exactly what the optimizers use for finding the best parameters. And then I think this is learning and evaluation. this thing here, which talks about Adam. This is just a specific way of finding the best parameters, which is quite good. And this actually, it says here, in practice, Adam is currently recommended as the default algorithm to use, and it often works slightly better than some other one. So that's why usually the recommendation is just to go with Adam. This is what we will do here. So we'll use Adam. And it has it has probably multiple parameters, but the important one for us is learning rate. So let's set it to 0.01. Let me just create a variable here, learning rate. So this is similar to eta in case of XGBoost. We'll talk about tuning this parameter a bit later in the next lecture. You can actually see in the next lesson is adjusting the learning rate. We're not there yet, so now we'll just use this value and see what happens. This is our optimizer. Then the optimizer needs to know how exactly it needs to change the weights. So how does it check that if it changes the weights, if the results are actually better? So let's say it took this value here and changed it. How does it know that a neural network actually learned something or it became worse? And for that, there is a concept of loss. Loss tells us how good the model is. So this is similar to metrics. So in Keras, the losses live in the losses package, and we see that there's a few of them. For our case, since we use, it's a multi-class classification problem, we use categorical cross entropy. For binary classification, we would use binary cross entropy. And then if we're solving the regression problem, we would use mean squared error. Remember we talked about mean squared error, which is a way of evaluating regression models. So categorical cross entropy is a way of evaluating classification models, in particular multi-class classification models. So it just outputs a number that is the lower the number, the better. And optimizer is trying to optimize this number. It's trying to make it as low as possible. And it's doing this by changing different values of our parameters. So this matrix W is parameter of the dense layer. You can have many different dense layers. Each of them has its own parameters. So optimizer is actually changing them, and it uses this categorical cross entropy to make sure it's actually improving things. So this will be our loss. For this loss, there is one interesting thing. So this is parameter from logits equals false. So we actually need to change it to true. And the reason for that, if we check the docs, this argument from logits, whether y prediction is expected to be a logits tensor. Yeah, and it says node using from logits true may be more numerically stable. So the recommendation actually is use from logits true, like we do here. And now let me explain what's happening here. Remember we talked about dense layers here. We have input here, then we have the output layer, and then we apply softmax to this. Softmax is called activation. It takes the input from here and turns this into a probability. And this input is called logits. This is the raw output of the dense layer before we apply softmax. Like if we have softmax, we have probabilities. If we don't include softmax, we have raw score. And so here we say that we want to use raw logits, raw score. So we don't use activation here. And let's say if we wanted to have the probabilities here, then we would use from logits false. And then here we would need to add activation softmax. So here we say that for this layer, after this dense layer is applied, we want to also invoke the activation function, a specific one, which is softmax. And the default one, activation is none. So it means that it doesn't apply anything. So it just keeps the raw scores like that. So we will keep the raw scores and we will use from logits false. Now we need to compile the model. This is something we need to do before training it. We just need to say that the optimizer we will use is this one, it's Adam, then loss is this one, categorical cross entropy, and then also metrics that we're interested in monitoring is accuracy. So at each step of training, it will show us the progress and it will show us the accuracy. So now it's compiled and we're ready to train a model. For that, we use the fit method. So we pass our train data source. Then we say for how many epochs we want to run. So one epoch is we go over the dataset once. So let's say we have our dataset. And our dataset consists of batches of 32 images each. Or the last one is not necessarily 32. It can be, I don't know, 17, It doesn't matter. All of them are 32 except the last one, because there could be fewer images. When we train a model, we usually apply to one batch at a time. So we fit a model on this batch, then on this one, then on this one, then on this one. This is like one iteration. And when we do it once, it's called epoch. When we say we want to have 10 epochs, it means go over the data 10 times. So let's go over the data 10 times. And then for validating this, we want to use the validation dataset. So let's execute it. Yeah, so there is a warning. I have no idea what it means. And now it shows what's happening. So it shows the current loss. And remember, the loss is this categorical cross entropy and then accuracy. So this is accuracy on training. So now one epoch is over and it's evaluating this. Okay, and says the accuracy on validation is this. I'll stop it. Actually, something is not right, so it should be higher. Let me check if I didn't forget anything. I think what I forgot to do is I needed to say training false here to make sure, like, it's not enough just to say trainable false. I also need to say training false here. Let me just put it in one cell so it's easier to execute it. So now I execute it. I'll remove this part and put this in one cell. Now let's run it one more time. So this time what I want to do is I want to be able to access this information. In case of XGBoost, remember we needed to capture the output. Here we don't need to do this because when we do model.fit, it returns a history object which contains all this information. So let's just put this into history and execute one more time. Something is wrong with accuracy. Let me stop it. So it should be way higher. Here from logits should be true. Let me execute the whole thing one more time. You see now accuracy is on the training data set grows a lot and then the loss is improving, it goes down. And the accuracy after the first epoch, after the first iteration is 75%. And here the accuracy means for how many examples, for how many images we got it correctly. You see it's already 80%. And yeah, so the loss is quite small on the training data set. And I think from now it will start overfitting a little bit. So now the discrepancy between validation accuracy and training accuracy is not that large, but the accuracy on the training keeps improving, but on validation not so much. So now it is overfitting already after 4 epochs. So I'll let it finish. I will edit this part. So for you, this will be momentarily now. For me, it will probably take 1 or 2 more minutes. Okay, it finished. So it seems to oscillate around 80. Sometimes it goes a bit up, sometimes it goes down, and the accuracy on the training is quite high. So it's almost 1. So it's clearly overfitting. So the results were saved in this history object. Let's take a look at what's inside. So actually history, and it contains all these values that we saw. So for us, the interesting one is accuracy. This is training accuracy and validation accuracy. So let's plot them. Plot. So then the first one, label train. And then for the second one, label will be validation. Let's plot the legend. Yeah, so we see that for training, it almost reaches 1. Yeah, so let's remove it. And for validation, it quickly reaches this 80. And then for the rest of the iteration, it just oscillates around 80. So sometimes it jumps quite high and then it goes down. So it will probably keep jumping. We train it for 100. And maybe at some point it will go down because clearly our network is overfitting. But yeah, we see how it behaves. And actually, after 1 iteration, let me add x ticks on the x. So I just want to have everything 0, 1, 2, etc. So not just 0, 2, 4, and so on. Okay, so we see that like it's already quite good. So 80%, I think, or slightly less, and then just keeps oscillating. So this one is good, but it just seems like a random fluctuation. And I'm not sure if it's really significant because you remember that the accuracy for on train was already like probably like 95% or something like this. So this one is probably overfitting. Yeah, it just got lucky. Okay, so it seems like with just these parameters, we didn't do much tuning. We already got a reasonably good model, 80% or like 82 after 2 iterations, 81, yeah, almost 82. It seems like good accuracy, but of course there are many parameters that we can change, we can try and tune. And in particular, like in case of XGBoost, like in case of gradient boosting, remember I said that the most important parameter is eta, which is the learning rate. The same is true for neural networks. So the learning parameter is the most important parameter that we need to tune. And this is what we'll do in the next lesson. So we will try different values of the learning rate and see which one is the optimal one. See you soon.